Kirchhoff's laws. In 1845, a German physicist, Gustav Robert Kirchhoff, developed a pair of laws which deal with the conservation of charge and energy within electrical circuits. These two laws are commonly known as Kirchhoff's current law, Kirchhoff's voltage law. These laws are used for analysis of circuits and in calculating the flow of current in different streams through the network and are applicable to both DC as well as low frequency AC circuits. 1. Kirchhoff's first law or Kirchhoff's current law or junction law. It states that any junction point in a circuit where the current can divide the sum of currents flowing into the junction is equal to the sum of currents leaving the junction. This law is based on conservation of charge. Let P be the junction. The junction is a point where two or more conducting wires meet. Let us consider a situation. The currents I1, I4, I6 are entering into the junction and I2, I3, I5 are the currents leaving the junction. Therefore, from Kirchhoff's current law, I1 plus I4 plus I6 is equal to I2 plus I3 plus I5. That implies I1 plus I4 plus I6 minus I2 plus I3 plus I5 is equal to 0. From this, we can conclude that at any junction, no accumulation of charges takes place at any junction, which means charge is conserved. Sign convention for battery and resistors. When a current is moving from positive terminal to negative terminal of a battery, EMF of a battery is considered as negative. When a current is moving from negative terminal to positive terminal of the battery, EMF of the battery is considered as positive. The direction of the electric current must be known to provide the sign to the potential difference of a resistor. The sign of the potential difference across the resistor is taken as negative if we move along the direction of electric current through the resistor. The sign of potential difference across the resistor is taken as positive if we move against the direction of electric current through the resistor. Kirchhoff's second law or Kirchhoff's voltage law or loop law. It states that in any closed loop network, the algebraic sum increases and decreases in potential difference across various components of the circuit is 0. This law is based on the conservation of energy. Example 5. In the given circuit, find the loop equation for all the potentials. A circuit with two batteries with potential difference V1 and V2 and resistances R1 and R2, R3 are connected as shown. Let the current flowing in AB is I1, CD is I2 and EF is I1 plus I2. Using the sign convention for loop ACDBA, the potential difference at battery B2 is equal to minus V2. The potential difference at resistance R2 is I2R2. The potential difference at resistance R2 is equal to minus I1R1. The potential difference at battery B1 is equal to V1. Resultant potential difference in the loop is equal to minus V2 plus I2R2 minus I1R1 plus V1 is equal to 0. Similarly, for the loop EFDCE, potential difference at battery B2 is equal to V2. Potential difference at resistance R2 and R3 is equal to minus I2R2 and minus of I1 plus I2 into R3 respectively. Resultant potential in the loop is equal to minus of I1 plus I2 into R3 minus I2R2 plus V2 is equal to 0. Similarly, for loop EFBAE, potential difference at the battery B1 is equal to V1. Potential difference at resistance R1 and R3 are minus I1 R1 and minus of I1 plus I2 into R3 respectively. The resultant potential in the loop is equal to minus of I1 plus I2 into R3 minus I1 R1 plus V1 is equal to 0.